Hello and welcome. What if you watching this today, at the end of this presentation, could design an aircraft? We'll get there at the end. First, let me take you through what we're going to talk about today. So first, we'll talk a little bit about what PhysicsX does and who PhysicsX is, and how we take our customers from traditional simulation-led engineering processes to AI-enabled engineering processes. Then we'll talk a little bit about our platform and examples on that platform of where we are doing this transformation with our customers. And we'll talk a bit about our foundational tech. These are large geometry and large physics models. And then at the end, we will be unveiling something here at reInvent, and something that is quite extraordinary, if we think, and that really takes engineering beyond human imagination. So PhysicsX is a deep tech company with just over 100 people, data scientists, simulation engineers, machine learning engineers, software developers. And we're working across three divisions, really. Our research group innovates, develops, builds architectures for geometric deep learning models that are relevant in engineering. Those architectures then get trained, and the training often happens with customer data, of course. So there's a close coupling between our research group and our products, and those foundational architectures sit at the heart of our platform, which is our product. And we'll have a couple slides on that and go through that so you can see exactly how the platform is layered. Delivery is super important. This is complex. What our customers operate are complex processes, and they're complex challenges, they're difficult challenges. And so at this very early stage of a transformation, it's not only software, it's software and people. And it really is about the people that work with our customers to help them innovate at the maximum speed. So we have a very strong delivery arm, again, composed of simulation engineers, data scientists, machine learning engineers, software developers that work closely, shoulder by shoulder with our customers to help them transform quickly and find the value pools that are really important, and then integrate that into their existing engineering tool chains so they can run the whole process. We work across these sectors with our customers. That's where our tech is relevant. That's where the legacy tech, which we'll describe in a moment, really is well established. So what we do in these sectors with our customers is we increase their speed of product development. And we leverage that speed to blow up optimization, to do a lot of optimization so that the product performs better. So we capture the essence of fast development and high performance development to deliver better products faster. We work in semiconductors with our customers to innovate the new semiconductors of tomorrow. In aerospace, to make aircraft lighter. In renewables, to make renewables machines more efficient, which enables and accelerates the necessary transition to a new type of energy for our planet. In materials, to make materials purer and consume less energy in the process of their manufacture. And in automotive, to make automobiles and motorcycles more efficient. So energy is tied across this whole sector. It is always one of the driving value pools. Now I want to talk a little bit about how engineering is done today in the leading organizations. For the last several decades, products have been developed with numerical simulation. This means you're solving the equations of physics which govern the behavior of objects. So on the left-hand side, you can see the Navier-Stokes equations, which governs the behavior of air and fluids, aerodynamics, fluid dynamics. And you solve these equations on a mesh. The mesh describes the geometry. These meshes tend to be millions to hundreds of millions of cells. And the reason they are so fine and structured over a geometry is that you have to solve those equations at every point of that mesh, and you can't have errors from one to the other. So the solutions have to converge, and that takes iterations. There are many steps, oftentimes thousands of steps for that to converge. So you can imagine 100 million cells, thousands of steps. You can imagine how often you have to solve those equations. And that takes a very long time. So we're going to show you something here. It's an artificial heart, but it's essentially a pump, right? And this artificial heart, it's about the size of your thumb. It sits in the left ventricle. And when the heartbeat is from a deceased heart muscle or heart attack, is no longer functioning, this pump pumps your blood around your body. And there are a couple of performance parameters that are relevant. Number one, it has to flow enough and not consume a lot of energy in doing so. It can't damage the blood by shearing it or letting it pool. That pooling will lead to thrombosis, which will lead to a stroke. Shearing it will lead to internal bleeding. All of those things require a trip back to the hospital. And it needs to run the whole day until you can recharge it at night, so it has to be energy efficient. So in this pump, there's a rotor. That's really at the heart of the heart pump. And that rotor has to be optimized for just those things I said. So on the left, we're coming back to now the simulation. You can see the result of a fluid dynamics simulation here, the mesh superimposed on that, and one calculates the physics, the flow, the shear, as the simulation progresses. Now, this is the de facto way, solving problems, predicting the behaviors of designs, products, objects, by solving numerical physics is the de facto way in which leading organizations develop their products, whether it's in aerospace and automotive or even here in medtech. Now, the reason that is it didn't used to be. It used to be physical development. You would build test cars and you would crash them into a wall to see if the occupants would survive that, crash test dummies. And then you would change the design, would make a new prototype car with new prototype parts and crash it into the wall again. It takes a lot of time and it's expensive. Destroying an expensive prototype car. So simulation has replaced that. Virtual crash simulation, now every auto manufacturer does that. This is how they develop the product to be faster. They do that. It doesn't cost anything except compute to smash the virtual car into the wall. And it's fast, right? So this was a quantum leap in performance in advanced industries to replace physical testing with virtual testing. And you can do that in most contexts, not always, but in most. And that has enabled the development speed, so the time it takes to develop a product from concept to production, to be compressed. Now, can we make another leap like that? Can we go even faster than that? So, can we train, in our context now, in AI, can we train a deep learning model, a geometric deep learning model, on all of the simulation data which has been developed over decades or can be regenerated quickly if necessary, similar to how a large language model is trained on volumes of text? Is there an equivalent large physics model to a large language model? And the answer is yes. We can build this, and in fact, to high accuracy. The reason it's a high accuracy because this is labeled data. This is highly accurate data already. All of that simulation data, all of that information on the meshes, all those flow fields, pressure fields, and all of that. These are highly validated simulations. Therefore, the data is labeled, and it's very high quality. So the models we can train are high-quality models. And the benefit is, though, the deep learning model is much, much faster. That heart pump simulation takes about 1.4 hours. And in some contexts, simulations are over a week per simulation long. So typically hours to days is a normal time to run one simulation. So can we go faster? Well, deep learning models, yes. It's not partial differential equations, it's linear algebra. Everybody knows they run in under a second. So when you can run the equivalent of a simulation that fast, you have the opportunity to optimize. You can change the design, run the model, inference, predict the physics, re-optimize the geometry, and you can do that very, very fast. And you can do that inexpensively. Simulations have to run on hundreds or thousands of CPUs for a long time. These model inference on a single large CPU like an A100. And even if you need more, you can split the graphs and all of that, but typically a single GPU will allow you to inference. So how do you train a large physics model? on the left-hand side of this image, it's a typical legacy process here. You run a CAE simulation. CAE is computer-aided engineering, so that can be CFD, computational fluid dynamics, or FEA, finite element analysis, or electromagnetic simulation, CEM. You run the simulation on the object, on the first geometry of that object, and you get a result. And then, okay, it's not good enough, so you optimize the geometry. You can do that by hand, or you do it programmatically, and you run this loop. And that generates data until, in the legacy process, you get somewhere that is acceptable. But in this, you might have to run 50 simulations or so to get to your target, because that's all you have time for in the few months that you have to develop this process, this product. But in the process of that, you generate training data. The training data, the input, again, is the geometry, the mesh, and some of the operating conditions like pressure difference. And the output is the physics, the pressure fields, the scalars, lift, drag, strain. Okay, great. As I said earlier, we built our own foundation models. They're on our platform. Our models are available. There's a few of them, a handful of different type of archetypes that are relevant for different contexts. But you can bring your own models to our platform. You can use models from Modulus if you want to, third-party models. Everything plays. You train the model, adjusting hyperparameters and so on until your correlation is acceptable. Then you can enter the design optimization loop, which is, again, geometry, but now not simulation, large physics model instead, and then optimizer. And this design optimization loop now, that whole loop takes 1 second to run, sometimes less. So you can run 100,000 in a day. At the very end, when you've achieved the maximum possible after a few days, let's say, the best geometry is then sent back to the simulation. That's your ground truth, and it's checked, just to make sure. And that's where it re-enters the engineering process, because that's an old de facto process that the geometry would have entered anyway. However, sometimes when you optimize, you get into areas of geometry, so you invent new types of geometries that weren't part of your training set, and they're a bit far away. When you're far outside your training set, the model has to extrapolate. And when models extrapolate, they tend to get inaccurate. Our models know their own uncertainty. We predict uncertainty quantification for our models. Once the uncertainty quantification for each one of these model predictions reaches above a certain threshold, when UQ is over some error, we kick off an automated retraining loop. That automated retraining loop then generates a geometry that is in that extrapolating regime. It runs one more simulation on that geometry, and it updates the model. So for sort of just to get a sense of scale, our models typically take between a couple handfuls to less than 100 geometries and simulations to be trained. So we're talking about a relatively small number of simulations and a relatively small numbers to re-optimize the model. So it's very, very data efficient, right? We then, at the end, have a well-validated model. It has high correlation. We have a well-validated design because the simulation carried out on the design, just one simulation at the end, validates it according to the legacy process and all the due diligence that engineering organizations need to do to sign off designs. Okay. So let's see that in action, what happens when we have a trained model and we run it through geometry creation, model inference, and optimization. So here's that rotor for the heart pump again. You can see we generate the geometry. This runs real time on one A100. Generate the geometry. The physics model evaluates it. An optimizer changes the geometry again based on the result. And all of that loop, you can see each iteration is one of those loops. It's about an iteration a second. On the left-hand side is delta P, it's pressure. And so as you increase the pressure difference, it just means the pump flows more. We're looking at one parameter here, but it's actually multi-parameter optimization. Blood damage has kept track of that. There's additional physics happening here that is also that you're not seeing, like thrust on the bearings and things like that. That is estimated just to make sure we don't exceed any of those thresholds. So in about the minute that I've been talking, we've made, what does that look like? Maybe a couple percent delta P improvement. Yeah. That's not bad, maybe a little over 1%. So, you keep going like that, you will reach eventually at some tangential state, but you will have done 100,000 simulations or optimizations in a day and really extracted the maximum performance out of this pump that is possible within the space that you have available. So if we put this all together, again, the loop, geometry creation, and let's dive a little bit more into how we generate geometry. Computer-aided engineering, parameterizations, computer-aided design, CAD, is the de facto way, the normal way that designs are done. Engineers specify all the curvatures and the distances between objects and all of that. Takes a long time to do that. You can mesh that part then, and you get a mesh, as you saw earlier, and you can distort this mesh. So that's a capability that we've built of mesh distortion. It's very fast. That takes a fraction of a second to distort the mesh. There are generative models. There are, not only us, other people do generative models, topology optimizers, and things like that. That's one way to generate geometry. But then there's a special way, and we'll get to that a little bit later on large geometry models, and I won't say more of that until I get there. As I said, we have deep foundation models that we train, and once they are trained to generalize well, these large physics models then can predict the physics. And then in optimization, there's classes of optimizers that we provide on the platform, Bayesian optimization, gradient descent, genetic algorithms. So let's talk about the platform a little bit. The PhysicsX platform is founded on a data unification layer. The data that is relevant is simulation data, but also laboratory testing data. I will show you an example of that in a moment. And operational data, so data coming from machines that are operating on the floor of a factory or from objects like helicopters that are flying. At the core of the platform are the large physics and large geometry models, which we'll describe in a moment. On the left-hand side is the developer environment. On the right-hand side, you see the integration points to the normal CAE tools, tools from Siemens, Dassault, ANSYS, and so on. And that's important because we have to exchange data with them. We have to kick off runs, retrieve data, and things like that. On top of that sit the solutions. And those solutions are really relevant for the sectors that you work in, so aerospace or automotive. It's often around shape optimization. There are solutions around, for example, structural optimization, system optimization, so several simulation tools linked in a chain that you want to optimize. We can do that. We have done that. Our customers are using that. The operations team, I said earlier, factor flow, I'll have an example dive into that. And even sales engineers are using these tools because they can very quickly predict the performance of, let's say, a hydroturbine or a wind turbine in the field under those local conditions under which they're trying to sell it. And that means they can sell a little bit more energy at lower risk. So let's now solve something on the platform. We'll demo the platform to you. And let's pick something difficult, because we like difficult, hard challenges. Let's pick a jet engine. So, jet engines are complex, and I don't understand them all. So, they're complex objects. And they're also very complex to simulate. I'm oversimplifying a little bit. Yeah, I'm just looking at one thing on this jet engine in particular. So let's dive into this jet engine, literally. The airflow is sucked in by the fan. It's then compressed on the compressor stage. And then these little bottles are the combustors, and they mix fuel and that compressed air and burn it. And then it exits into the turbine stage at the end, and the expanding air causes the turbine to spin and produce the thrust. So we're just going to look now at the combustor. So it's a canister with holes. At the entrance, you can't see it, it's got mixing blades, stationary blades that mix the fuel and the air, and they've got complex shapes. And the can can, what's the shape of the can like? There's a lot to optimize around there, lots of holes in them. So a lot of parameters to optimize. And it's multi-physics, right? We've got airflow, we've got thermal physics, We got chemistry, we're combusting stuff, right? So there's chemical reaction equations that have to be solved. There are material properties that have to be obeyed, constrained, temperature limits, things like that for material properties, for stress and strain and thermal fatigue. So this is complex. How can AI possibly solve this? Okay, so now we're in the interface of our platform. Here's the starting geometry of that combustor. On the right-hand side are the geometrical parameters you can vary. This is how this has been set up. So there's, I don't know, 8 or 9 of them that can be varied. And let's see how this is done, right? Let's change a couple of these geometries on the right-hand side. So adjusting, can't see it from here. Adjusting a few, hit run, and there, less than a second, this is the result. Now this is real physics. These are the real performance parameters. They're low efficiency of 0.3, high temperatures everywhere. Clearly not a good design. So let's re-optimize here, just changing, making it a bit longer. Hit inference again. Okay, a little bit better, 0.4, not great. Temperature's a bit more under control on the exit now. Now, so I could go through this manually, but that takes a long time. How can we do that programmatically? Can we do this hands-off? Absolutely. Let's have the part optimized by itself. So now in the background, this process that I described earlier is running. Geometry creation, large physics model inference, optimization, looping this, and while I'm talking, there's only time for, I don't know, a couple dozen or so runs. So these are the results. On the bottom axis, you have efficiency, so essentially power produced. On the vertical axis, you have emissions, and lower is better. So on the left-hand side here is a very low emission point. These are the low, each point is a geometry. It's a full solution. You can see the solution there in the top left corner. And, let's pick one in the knee of the curve that makes sense. It's still low emissions, but has high efficiency. And if I look at the efficiency number, it's 0.7. Let's load that model. You can see it looks very different. Much longer, skinnier. Hole locations are different. You can see the turbulators of the blades, whatever those have shown up now to be. But you can see the whole flow field is much, much better. The temperatures are very contained. Everything is burned, right? There's no more burning near the exit, so efficiency is high. So in a matter of a couple minutes or so, maybe a minute, we got to somewhere that with the legacy simulation would have taken us weeks. And we can go more and see if this Pareto front, this curve, even pushes us into yet a better direction. So what this means is that we can take the time-consuming process of numerical simulation, compress it greatly, and optimize designs much better. Now, we talked about this optimization in the context of product development. But there are other contexts in the product lifecycle that are relevant that we'll get into. So in product development, just some other examples. For example, we have worked in things like eVTOL, Formula One cars, our background, passenger car wheels for flow and strength, wind turbines, and even nuclear fusion, which is really hard physics, but the models can learn that. The next stage on product, well, I'm going to walk you through one example, but I got to keep an eye on time a little bit. So this is now structural simulation. There's a tire. It's a tire for racing cars. You're not actually seeing that a real tire here, but for a racing car. And when a racing car goes around the corner, the tire deforms because it's very sticky, lots of load, tire side wall changes. And when that happens, the airflow changes. So when you want to do a CFD simulation of that car, you need to know the shape of the tire in that cornering condition. In a corner, you want to have lots of downforce. On the straight, and have low drag. Okay, so you need to know the shape of the tire. Well, it takes about 14 hours to run one of those shape simulations. Just one set of loads at the contact patch, and you get the new shape back 14 hours later. You can't iterate, right? That takes really long. And there are dozens and dozens of these conditions which you have to reproduce around the racetrack. So can we go faster? Yes, we trained a model on only 35 of these finite element results. And you can see the results of the model here. Correlation of 98%. By comparison, a GP, we trained a GP earnestly to benchmark against that, had a correlation of 59%. A shape error of no more than 1.5 millimeters across the whole shape of the tire compared to the ground truth for all of those different loading conditions. So highly accurate. A GP had 9.5 millimeters. So geometric deep learning really accelerates the ability to have accurate models. But even more interestingly, there was lab test data. The shape of the sidewall was measured in a lab test where the tire was exposed to the same loads. And we trained on that as well. And you can see that in the right-hand graph here. The blue line, and this is not blown up. This is how much these tires distort. The blue line is the undistorted shape of the tire when it's not loaded. Oh, I should say one thing about these tires. These are complex, right? Number one, you have rubber, viscoelastic material, nasty material. Then you have Kevlar belts in these tires. Then you've got centrifugal forces acting on them. And you have a contact patch, which you can see is flat here once it's loaded. And you have inflation pressures and temperature. So the model has to know about all of these things to give you the right answer. So you can see the flat contact patch once it's loaded, and you can see the sidewall distortion here. And the colors are difficult to see, but basically the green line here is the model prediction, and the lab test data is the red line that is literally right underneath the green line. The FE data is just a little bit to the inside purple there. And so you can see retraining it with the lab test data actually gave us that last bit of accuracy that we needed. And that is fantastic because these models, they train on data. You represent the data on the same mesh. The model doesn't know whether it's numerical or laboratory data. I'm going to skip a little bit. I'm just going to say on this one, this is a structural optimization of a heat exchanger. A very complex heat exchanger, conformal heat exchanger, sits around an aircraft, commercial aircraft. And there it needed a complete virtual prove-out. So multi-physics, this was flow, temperature, both external air, oil, and burst simulations, burst validation, and even vibration optimization. So the design was taken from a standard manufacturing process of machined and braced part to additive, where we had a lot of geometric design freedom and could really run our geometry models very, very fast. Let me go a bit quicker here. Manufacturing. This tech is very relevant in manufacturing. For example, we optimize casting. Here's an example from a jet engine QA process. You saw earlier in the compressor stage of the jet engine, you have these blades. They have to conform to the drawing. They have to be balanced around the compressor ring. They have to produce the thrust. So the way each blade is dimensionally scanned, and when it falls outside the range of dimensions, the error that is allowed within the drawing, it's scrapped. But you don't really care about whether it conforms to the drawing. What you care about whether it makes the thrust that it's supposed to make, right? So we trained a model with our customer very, very much on this data, and the scan is done, and within a second, the operator, the technician, knows whether it conforms to a thrust requirement or not. Does it fall within that band of not too little and not too much thrust? And then if it does fall outside of the band, it's scrapped. We reduced the scrap rate by 70% doing that. They were scrapping far too many parts. Not only that, the models are differentiable, so you can find out the highest sensitivity area for performance. That's where the manufacturing process has to be accurate. And in areas where the performance isn't affected by a dimensional variable, you can relax the manufacturing process. So that's also really valuable information to feed back in. Operational metrics. Here in particular, this is aluminum smelting, huge pools, the size of swimming pools, full of molten aluminum. And you want to have the highest quality concentration of aluminate. So it's very important to keep the uniformity and the temperature for the aluminum to form in these pools very uniform. There's feeder rates that feed in the aluminate. And you want to use also the minimum amount of temperature to create that high quality aluminate. And here you see you see two images from, and this is hydromagnetic simulation. So again, very complex physics simulation that we're reproducing with a large physics model. You can see the difference between the large physics model prediction on unseen data and the simulation. Simulation takes 72 hours. For one condition, for one operating condition, the LPM takes under a second. Now, this is being used now. This is being integrated into the control systems of this materials manufacturer in order to operate on the production floor. So again, in an operational context, large physics models can be plant representations that can integrate into control systems real time. Not all control systems, if the control system has a 1,000 hertz update rate, no, that's too fast. But if the update rate is tens of hertz or something like that, that's possible. And you design the physics model to operate that quickly. This is quite cool. This is a virtual sensor. The application here is virtual sensor. So helicopter OEM, who we've been working with for about 2 years, is using our technology across a number of applications. In this particular case, these blades flap. They're free to move this way as they're loaded and unloaded. And when you develop a helicopter, you want to know what that flap angle is. And that's a very expensive kit of piece to put on the helicopter. It's, they don't have many. And then you have to perform all of these special flight tests to all the operational conditions and all of that. Adds up to a lot of time and money. We trained on some of this data, and then we placed the physical sensor with a virtual sensor. And the virtual sensor was only driven by the flight conditions, so rate of lift, angle of attack, all this sort of thing, and pilot inputs. Nothing else. So it didn't require any other sensors that weren't already on the normal helicopter as it is. And it predicted the blade flap angle as a function of time. And you can see that here. So there's the predicted signal in blue and the true filtered signal from the sensor. And it's not perfect, but it's pretty close. It already, in terms of understanding the fatigues and the cycles that this goes through, it's a great virtual sensor in lieu of something that's very expensive and time-consuming. I think the most interesting stage is innovate. So this is where you have your concepts for your new designs, your new ideas. How can machine learning and deep learning possibly help in that? Right? We're training on existing data, existing simulation models. Well, let's get into this. I think it's really exciting, and we want to come back to another element of our foundational tech, which is large geometry models. So what we do is we replace computer-aided design engineering with large geometry models. And the way we have done that is we've trained a large geometry model. And this is the largest geometry model for engineering. We trained on 25 million geometries, everything we could find, everything that we could generate. And we learned what is foundationally true about geometry from that training. This model was trained on AWS, Elastic Compute, as part of our GenAI award and consortium. We learned encodings of these geometries into a vector. So take a big mesh, millions of cells, and you can encode it into a vector of a few hundred numbers, typically. That's incredible. That's an incredible amount of data compression. And it takes a deep learning model to learn this encoding to be maximally accurate to within this dimensionality reduction. The space of vectors, the vector is called a latent vector, and the space of vectors is called a latent space. And in this latent space, every point is a geometry. We just collapsed the vector here into a plane so it can be seen essentially. So each point is a particular type of geometry. And you can think of the latent space as a feature space of sorts. It's a space that's learned. It's not humanly imposed. So it's a bit hard to describe it, but we think of it as a feature space. Now, let's see what we can do with this latent vector. If we put a large geometry model, so this model can now encode any geometry into a latent vector. If we take a geometry, a mesh, let's say, and we encode it, and it represents a point in the latent space, we can then decode it again. We can either decode it into another type of geometry or the same geometry, and that's actually how we train to make sure that these meshes, after encoding and decoding, truly overlap, or into physics. And that's where it gets interesting. Because now we have a latent vector of a few hundred numbers that learns a lot faster, right? You can inference a lot more accurately, train it more accurately, back to the physics, which are fields, pressure fields, volumetric fields, scalars. Now, what's really cool is that, this latent space, the space of geometries, there you see the geometries that we've used, let's say, in the training, right? So you know what's in the space where you trained, right? But what's in the white space? It's a space, right? Yeah, there's data in the white spots. What does that look like? So, there's a geometry here on the left of an aircraft. What about the geometry of a bird? Where's that? And what's between the shape of a bird and an aircraft, and how does that fly? So let's do that. We're doing a random walk through this latent space. We go from the aircraft to some stubby object, to a bird, to a glider, a stubby glider, and then that grows a tail, and it's back to an aircraft, which then slowly goes back to a stubby thing and a bird. So we're repeating this random walk at every point of this latent space, including all the white spaces. So we see the physics on the right-hand side, the pressure distribution and the drag. And I want to just emphasize, this is real. This isn't a Figma thing. This is real physics, validated, run, accurate. And this really sort of sums up sort of a new world of engineering, doesn't it? I think large geometry models and large physics models have arrived. They're real, and they're going to change the way engineering is practiced. And that's what our customers are doing now. Now, at the beginning of the talk, I promised you that you could design an aircraft. So let's do that. Let's finish with that. Our expert simulation engineers used AWS, Elastic Compute, and Siemens CFD and FAA software to generate a huge data set of physics. Tens of thousands of geometries in our latent space were evaluated for the physics, and we trained a large physics model on that. So today, we're unveiling the result, and we call it AI.RPlane, or Airplane. Airplane is the world's first large geometry and large physics model for flight. It's one example, though, of how this type of process will transform engineering. So let's dive into Airplane. So what you're seeing here is the latent map. Again, the latent space. I have to click run so it runs. And some of the geometries here on that latent space. And right now we're looking at lift versus drag. So light blue means high performance. There's also stability that we're looking at. So aircraft stability, there's cargo volume. Okay, so now we can set some sliders on the left-hand side here to sort of narrow up where we want to be, maximum wingspan, so it fits in your garage or whatever. The power of the engines, the thrust, some other parameters, how much weight it needs to carry and whatnot. Let's regenerate, and there's the latent space. Here are all the geometries that fit those requirements we've just set, and we can explore them. So there's the first one, kind of looks like a bird, sort of. And there's another one, and that looks like a glider. Has different dimensions, obviously. And there's one here, that's maybe like a flying wing. We could also click in the white spaces, and there would be a new geometry generated. But let's pick one of the ones that we just looked at. I think that's the first one. And there's the physics for it. There are the physics fields instantaneously. Well, what's the structure look like, right? We've seen lift over drag. We've seen the pressure distribution right now. What's the optimal internal structure look like? Now we're optimizing the thickness of the wings and the fuselage to support the load. So first, we're doing an evaluation of the stresses. So when this is done, we see a stress distribution. And then at the same time, it runs that loop of geometry, thickness, large physics model for finite element analysis, optimization. Okay, so this is now the stress distribution that we see. And usually you would have high stresses here between the wing and the fuselage, and this doesn't. And the reason it doesn't is because it's increased the thickness of the wing. We're looking at thickness now in that area. So it's mitigated it to the maximum level of stress that's permissible for that material. Now, you can now go and export the shape, and you can go 3D print it, and we've done that and launched them off little launchers and flown them, and that good old fun, and made sure they were stable and learned a lot from that. But what's really cool is you can do this yourself. So here at reInvent, we're releasing Airplane for public use. Anybody can go use it. And we would love for you to do that and offer us that feedback. Really looking forward to that. It's basic right now, right? You've seen what it does. There's a bit more as you play with it. But over time, we're going to increase the content of that to make this more and more realistic. So we're going to add internal structure. We're going to add cargo protection and cargo positioning and cargo support. We're going to add selections of powertrains that you can download, so real powertrains, commercially available powertrains. We're going to add control surfaces, flaps, and the control mechanisms for them, the autopilots, to do that. So that will take time, but please keep coming back to this and keep checking back for updates. The upshot from this is that AI-accelerated engineering is real. We have enough proof points, something over 60 proof points in advanced industries where this is working and delivering value in design, in manufacturing, and operations. So we are delivering this to our customers are operating, and we can do a lot more of that across advanced industries. Now, the real question is not if advanced industries will adopt and transform that. The question is how fast. Those of us who lived the digital revolution from physical to numerical simulation know this is a long transformation, but it happens because of the value and speed it delivers. Exactly the same thing here. The value and the speed that it delivers is absolutely worth it. But I don't think this will take decades. This will take a number of years, because the pace of AI development and value creation is immense. So we firmly believe, and our mission is, that to change engineering the way it is practiced, and we believe this will happen, and will happen quickly. And engineers and their organizations will have the superpower of AI at their fingertips in the near future. And in fact, some already do. Thank you.